everyone. Welcome to this tutorial on how to perform a one-sample t-test using Jamovie. So I will guide you through this analysis using a simple data set. Today, we will explore whether the average weight of a group of students differs significantly from a hypothesized value. Okay, let's get started. Before we jump into Jamovie, let's briefly explain what a one-sample t-test is. So this statistical test compares the mean of a single sample to a known or hypothesized population mean. It helps us determine if our sample's average is significantly different from a specific value. For instance, if we want to test if the average weight of students is significantly different from 25 kilograms, so we use this test. So let's take a look at our data set. I will share my slides. Here is our data set. As we can see, we have here our sample 20 students, and we have also here the weights that we are going to use. Okay, so let's upload this, or let's load this data set to the Jamovie. Okay, and then the next one is our data set for weights. Okay, so here it is. So after that, this column, the weights. So as we can see here, our measure type is nominal. So we change this into continuous because this variable is numbers. So let's go back. And then after that, we will go to the t-test. And we will choose the one sample t-test. And then as you can see, we have here our variable. Since our variable is the weights, which is the column, we will drag this one to this box, and Jamovie will generate the result. Okay, so after that, we will need to specify the hypothesized mean. So let's test whether the average weight is significantly different from 25 kilogram. Okay, so let's look at the field test value, which is here, and the hypothesis. We will enter here the number 25, and then this tells Jamovie that we want to compare our sample mean against 25 kilogram. Okay, so after that, the descriptive, we will click the descriptives. Under the descriptives, the descriptive plots for us to make our analysis more clearer. So we can add these descriptive plots, and then the mean difference, the confidence interval, which is the 95%. Okay, so as we can see here, we have the result that generated by Jamovie. So the first part in descriptives shows the sample size n, which we have 20 students, and the mean weight, which is 25.25, and then the standard deviation 2.19. And then in t-statistics and p-value, so the t-statistics indicates the size of the difference relative to the variation in our sample, while the p-value tells us whether this difference is statistically significant. And this 95% confidence interval gives us a range in which we expect the true mean to fall based on our sample data. So, this is our output that shows that our mean weight is 25.5, and then our t-statistics to 1.04, and then the p-value is 0.311. So the mean weight is slightly higher than 25 kilogram, which is 25.5, and then our t-statistics of 1.04 suggests a small effect size, while our p-value of 0.311 is greater than 0.25, 0.05 rather, indicating that the difference is not statistically significant at the 5% level. So this means that we fail to reject the null hypothesis, suggesting that the average weight is not significantly different from 25 kilogram. And we have also here the plots. So this will help us visually assess the distribution of weights and how it compares to the hypothesized mean of 25 kilogram, as we can see here. Okay, so that's how we perform is one sample t-test in Jamovi. Thank you everyone for watching, and God bless. Hello again everyone, welcome to this tutorial on how to perform a paired sample t-test using Jamovi. So for today, we will be analyzing a data set that examines student scores before and after the holidays to see if there's a significant difference in their performance. Okay, so let's dive into it. Okay, I will share my screen. Okay, as we can see, I have already prepared our data set that we are going to use. And then we will use this data, and we will just load this one to the Jamovi. And I have already also prepared the Jamovi. Okay, so after loading, so we will just change this nominal into continuous, since this data loaded is should be labeled as a numeric variable. Okay, and then this one also we will change this into continuous. Okay, after that, so Jamovi will automatically detects numeric categorical data types. So if you notice, so any discrepancies, you can manually change the data type by clicking on the column on here, the header. So after that, we will go to the t-test here, and then we will select the paired sample t-test. Okay, so as we can see, we have here the paired sample t-test and then the paired variables. So we will drag the points before holidays to this box, and the second one is the other box, second box. Okay, so This means that we are pairing these two variables because we want to test if there is a significant difference in scores before and after the holidays for the same group of students. And then after that, we will look at the paired sample statistic table. Okay, so we will click the descriptive, and then the mean, the effect. Okay, so as we can see here at the right side, so the mean difference, we have here the mean difference. This shows the average difference between the two sets of scores. So we have the mean difference of negative 3.30. So this is their difference. And our p-value, which has negative 1.39, and our p is 0.197. So these are the critical statistics we need to interpret the test results. So if the p-value is less than 0.05, so we reject the null hypothesis, indicating a significant difference in student scores before and after the holidays. But if the p-value is greater than 0.05, so we fail to reject the null hypothesis, meaning there is no significant difference. So as we can see here, our output, we see that the mean difference in scores is negative 3.30, and our t-value is negative 1.39, and our p-value is 0.197. So since our p-value is greater than 0.05, so we can fail to reject the null hypothesis. So this means that there is no significant difference in the scores before and after the holidays. Okay, so for more visualization, we can add a descriptive plots. Okay, which we can analyze. We will see a graph showing that the mean scores before and after the holidays. So here we can clearly see if the scores have improved, decreased, or stayed the same. So based on our paired sample t-test, we found that not significant difference in the scores before and after the holidays. There is no significance. So this suggests that the holidays had no impact on the students' performance. Okay, so that is how we show the results of the paired sample t-test. So thank you everyone for watching, and God bless.
Hello again, everyone. This time we will perform an analysis using the Jamovi for one-way ANOVA. Okay, first that we are going to do is I will share my screen. Okay, so I have already here prepared my data set, and we will open a Jamovi. First that we are going to do is to load our data set here at Jamovi. Okay, let us go to our data set. So here is the dataset of ANOVA. So we will just copy these two columns and then paste it to Jamovi. So as we can see, we have already uploaded our data set. So after that, after setting up our data set, so we will conduct the one-way ANOVA test, and we will navigate to analyze the ANOVA. We will click on the ANOVA and we will choose the one-way ANOVA. Okay, as you can see here, there is a variable, but before that we will just first change the name of this header, the reaction time, and the group. So the first one is the group. We will just manually change this, and the B, which is the reaction time, we will just copy and paste. Okay, so and then this reaction time, we will change this into continuous because it is a number. So here it is. We will click the ANOVA, and here it is. We will drag this reaction to our dependent variable box, and for the group is for grouping variable. And then after that, after dragging, so in this analysis panel, so we already drag the reaction time and the group, which is our grouping variable. So we will just we will just check the homogeneity of variance, so we can enable the homogeneity test. So this is under the assumption checks. After that, as we can see, we have here the results of the assumption checks. So we will interpret the results first in this in our one-way ANOVA table. So the ANOVA table shows the if statistics and the p-value. As we can see, our if statistics is 3.23 and our p-value is 0.055. So since our p-value is less than our alpha level of 0.05, so we reject the null hypothesis, indicating that there is a significant difference in reaction times between at least two groups. And then after that, in our assumption checks, so we can see here the F statistics is 1.26 and our p-value is 0.184. So since our p-value is greater than 0.05, so we fail to reject the null hypothesis. So this means that there is no statistically significant difference in reaction times among these groups. Okay, so after that, we will conduct also the analysis, the post hoc analysis. Okay, so here it is, and then we will check the Turkey. Okay, and then after checking, so our the Jamovi give the results, Turkey post hoc test. So this is our analysis of this. So since we identified the difference, so after conducting our post hoc test. So the results show that we have our mean difference in group B and C, and our p-value in B and C, and our mean difference p-value as you can see. So this shows a noticeable difference compared to the other group, aligning with our statistical results. So our one-way Jamovi analysis using Jamovi helps us determine if there were significant differences in reaction times across groups A, B, and C. So that's how we conduct or perform our one-way ANOVA analysis using Jamovi. Thank you for watching and God bless.
Hello again, everyone. Welcome to another statistical analysis using Jamovi. So today we will be conducting a person correlation analysis to explore the relationship between two continuous variables, height and weight. So the data set we'll be using includes 10 pairs of height and weight measurements. And we want to determine if there is a significant linear relationship between these two variables. And but before that, I will explain first. The person R is a statistical measure that calculates the strength and direction of the linear relationship between two continuous variables. So the value of R ranges from -1 to +1, where R is equal to 1. This indicates a perfect positive correlation, and R is equal to -1 indicates a perfect negative correlation, and R is equal to 0, which indicates also no linear relationship. Okay, so let us start. I will share my screen. I have here already our data set that is prepared, and this data set we will import this one to Jamovi. Okay, we'll open the Jamovi app. A while. So as you can see, our data set consists of two columns, which is the height and the weight. Okay. So we will just input our data set here. So after that, we will change our variable. So this is the height. We'll change this into continuous, and the B column, which is the weight, we'll also change this into continuous. Okay, go back to our data set. So here it is. So after that, we will perform the person correlation analysis. So we are already in analysis, and then we will click the regression. We will choose the correlation matrix. So this we have here our two variables. We will drag these two variables, the height and weight, to this box. As you can see here, this also tells us or tells Jamovi to compute the person correlation coefficient for this variable. So here it is, our variable. So to visually check for
linearity, we can also create a scatter plot. So we have here our plot. We will click this one, and then we can see the linear trend between height and weight. Okay, so let us go back to our output. So we have here the correlation matrix that shows the Pearson correlation coefficient R and the p-value for testing the significance of the relationship. So for our data set, so we have here, this is our Pearson R, which has a value of 0.860, and then which we can say that this value, which is positive, there is a strong correlation or positive linear relationship between height and weight. So the positive sign indicates that as height increases, weight also tends to increase. And as we can see here, our p-value is 0.001, which is less than our significance level of 0.05. This also suggests that a statistically significant correlation between height and weight. Okay, so in conclusion, our Pearson correlation analysis showed a significant positive linear relationship between height and weight. So this implies that in our sample, taller individuals tend to have higher weights. So Pearson's R is a powerful tool for identifying relationships between continuous variables, and using Jamovi makes it simple and intuitive. And that's how we conduct our Pearson R, or our Pearson correlation analysis. Thank you for watching, and God bless.
Hello everyone, welcome to another tutorial series. So today, I will guide you through performing a simple linear regression analysis using Jamovi. We will be exploring how age can predict glucose levels using a simple data set. But before going further, let us briefly discuss what is simple linear regression. So it is a statistical method used to examine the linear relationship between two continuous variables. So in our case, we want to see how well we can predict glucose levels based on a person's age. Okay, so I will share my screen, and then here it is. I have already prepared my data set. We will just copy this one or load to our already opened Jamovi. Okay, and then we will change the header. This is age, and then we will change this into continuous. And then our column B, which is the glucose level. Still, it is continuous. Okay, after that, we will go to the exploration and then scatter plot, and we will choose the linear, and then we will drag this glucose level to x-axis and the age to y-axis. So Jamovie will automatically generate the scatter plot. Okay, so next, we will go to the regression and then linear regression. We will drag this dependent variable to this box and the age to covariates. Okay, after that, we will go to the assumption checks and we will enable the following: autocorrelation test, normally test, QQ plot of residuals, and residual plots. And for the model fit, we will click on the F-test. In model coefficient, we will enable the ANOVA test. Okay, so let's go to the interpretation of the results. So the scatter plot here is what you can see, suggests a positive correlation between glucose level and age. As glucose level increases, age tends to increase as well. So the line of best fit visually reinforces this trend. However, the correlation doesn't appear to be very strong. So there's a considerable scatter around the line. So the data suggests a weak positive correlation between glucose level and age in this small sample. So more data points would be needed to confirm the strength and significance of this relationship. And then, so after this one, this okay, so this linear regression and our model fit measures. So this image here, the results of regression analysis examining the relationship between age and glucose level in our Omnimous ANOVA test. So there are sum of squares represents the total variability in glucose levels. So it's partitioned into variability explained by age and unexplained variability, our residuals. And the DF, or the degrees of freedom, so the number of independent pieces of information used to estimate the variability. So for age, it's 1. So for residuals, it's 4. So our mean square, this is the average variability calculated by dividing the sum of squares by the DF, and our F statistics, which attests the overall significance of the model. A larger F statistics indicates a better fit, and our p-value associated with the F statistics, the p-value of 0.240 indicates that the model is not statistically significant at conventional levels, typically 0.05. So this means that age does not significantly explain the variation in glucose levels in this model. So go back to our model fit measures. So this table shows the estimated coefficients of the regression equations, and the equation is of the form glucose level is equals to intercept here in our model coefficients, and then plus age, and our predictor, which is our independent variable, the age, and then the estimated coefficient for each predictor, and the SE, the standard error of the estimate, and the T, testing the significance of each predictor's coefficient, and the P value associated with the T statistics. So at the intercept of 63.956 indicates the predicted glucose level when age is 0. So the coefficient for age 0.411 suggests that for every 1 unit increase in age, the glucose level increases by 0.411 units. However, the p-value of 0.240 for age indicates that this effect is not statistically significant. So the regression analysis suggests that age is not a statistically significant predictor of glucose level in this data set. So the overall model is not significant. Our p-value is 0.240 and the coefficient for age is also not significant. Okay, so our normality test naman, in statistic, the Shapiro-Wilk test statistic is 0.846. So this value itself doesn't tell us much without comparing it to critical values or looking up the p-value. So our p-value is 0.145. And this is the most important part. A p-value greater than a significance level 0.05 indicates that we fail to reject the null hypothesis. So in simpler terms, there's not enough evidence to conclude that the residuals are not normally distributed. So in this case, the p-value of 0.145 suggests that the assumption of normality of residuals is not violated. Okay, well, this QQ plot, so if the residuals are normally distributed, the points on the QQ plot should fall approximately along a straight diagonal line. So in this plot, the points are reasonably close to the line, especially in the central part of the distribution. So there's a slight deviation at the higher end, but it's not dramatically severe. So both the Shapiro-Wilk test, our 0.145 and the QQ plot suggest that the assumption of normality of residuals is reasonably met. So these residual plots versus fitted values, ideally, the points should be randomly scattered around a horizontal line at 0, indicating that the residuals have a mean of 0 and are independent of the fitted values. So in this plot, there's some suggestion of non-constant variance. So the spread of the residuals seems larger at higher fitted values. So this violates the assumption of homozygosity. The pattern is not strongly pronounced, but it's noticeable. And the next plot, residuals versus a glucose level. Similar to the first plot, we look for random scatter around 0. So this plot also shows some indication of non-constant variance. The spread of residuals appears larger at higher glucose levels. So again, this suggests heterodicity, violating the assumption of constant variance of errors. So both residual plots raise concerns about the assumption of homozygosity. So the residuals exhibit a pattern where the variability increases with both the fitted values and the glucose levels. So this suggests that the model's assumptions are violated. So transforming the dependent variable or using weighted least squares regression might be considered to address this issue. So the violation of homozydasticity can affect the reliability of the standard errors and p-values from the regression analysis. So that's how we conduct our simple linear regression using the Jamovi. Thank you everyone for watching, and God bless. Good day again, everyone. Welcome to our Jamovi tutorial series. So this time we will conduct how to analyze the multiple regression using Jamovi. Okay, so but before that, we will just explain what is a multiple regression. It is a statistical technique used to predict the outcome of a dependent variable based on several independent variables. So, y is a dependent variable. So, in our case today, it is our weight. And the x1r, x2r, and x3 are the independent variables, which are the height, age, and gender. And b0 is the intercept, and then b1r, b2r, b3 are the coefficients for each predictor, and e is the error term. Okay, so we have our data set. So we have 10 participants with the following variables. So the weight, which is the weight of the individual, the height, and the height of the individual in meters, and the age and the gender, code as male and female. Okay, so let's proceed to load our data set to Jamovi, and then we will just copy this one and load it to Jamovi. So here it is, our data set. So we will just change the header of this, and this the weight, and we will change this into continuous, and then our height also, it is a continuous, and the age continuous, and to gender we will leave this as is, as nominal, because it is text. Okay, so after that, so we will conduct our multiple regression analysis. So we will click on the regression, and then we will choose the linear regression. Okay, as we can see here, let us drag our dependent variable to the dependent variable box. Our dependent variable is the weight of the individual, and our covariates is the height and age. Okay, so here it is. So these are our independent variables. So in our data set, as you can see, gender is not on the covariates box. So Jamovi automatically detects it as a factor. So we will drag the gender variable to the factor box. So we already ensure that as a categorical predictor, So gender belong to this tab factors. Okay, after that, we will click on the model fit measures, and then we will click on the adjusted, and then the F fast, and then the model coefficients, we will click on the ANOVA test, the confidence interval, the standardized estimate. Okay, here nothing here in estimated marginal means. In assumption checks, we will use, or you will enable the normality test, the QQ plot of residuals, and the residual plots. Of course, the Cox distance. Okay, so that's it. Reference level, nothing here. Model builder. Okay, so let us proceed to our interpretation of the result. So in our linear regression table in model fit measures, so the model shows a significant overall fit, which is the p value equals to 0.030, indicating that the predictors height, age, and gender collectively explain a significant portion of the variance in the dependent variable, the weight. So the R squared, which is the 0.754, suggests that approximately 75.4% of the variance in weight is accounted for by the model. And then we have here our individual predictor effects. So in age, it is a significant predictor of weight. So our p-value for age is 0.041. So the positive coefficient suggests that as age increases, weight also tends to increase. And our height is not a significant predictor of weight because our p-value is equals to 0.137. So the p-value is greater than our significance level of 0.05, indicating that the effect of height on weight is not statistically significant. And in our gender, it is not also a significant predictor of weight because our p-value is 0.162. This p-value is greater than 0.05, suggesting that gender does not significantly affect weight in this model. So the analysis is based on relatively small sample size, our n, which is equals to 10, which may limit the generalizability of the findings. So the model also assumes a linear relationship between the predictor and the dependent variable. If the relationship is nonlinear, the model may not accurately capture the true effect. So also other potential confounding variables that might influence weight are not included in this model. And this also, the image of model coefficient weight shows the Cox distance values. We have here our mean, median, standard deviation, minimum, and maximum. Okay. In summary, so this analysis here suggests that age is the only significant predictor of weight among the variables considered. However, caution is warranted due to the small sample size and potential limitations of the model. Okay. The next one is this QQ plot. So we will interpret this plot. So this plot compares the quantiles of the standardized residuals to the quantiles of a normal distribution. So ideally, the points should fall approximately along a straight diagonal line, indicating that the residuals are normally distributed. So in this QQ plot, most points are reasonably close to the diagonal line, as you can see, suggesting that the residuals are approximately normally distributed. However, there's a slight deviation at the upper end, here, the dot, indicating a potential departure from normality in the tails of the distribution. So this deviation is not extremely severe, but it's worth noting. And then the next one, our residual plots. So this plot displays the residuals against the fitted values. So it helps to check for non-linearity, non-constant variance, and outliers. So the residuals versus fitted plot shows some scattering of points around zero, suggesting that the assumption of constant variance is reasonably met. So there isn't a clear pattern indicating non-linearity. However, there are a few points that stand out as the potentially high leverage or influential points. So these points are worth investigating further. The next plot, residuals and the versus order plot. So this plot shows that residuals plotted against their order in the data set. So it helps to detect patterns or trends in the residuals over time or sequence. Because only a portion of this plot is visible, a complete interpretation is not possible. However, the visible portion, there is no clear pattern suggesting autocorrelation or other time-related issues. The next plot displays the residuals plotted against the height. Ideally, in a well-fitting model, the residuals should be randomly scattered around zero, with no clear pattern or trend. So the presence of patterns or non-randomness suggests potential violations of the model assumption. Okay, and based on this plot, the assumption of constant variance seems reasonably met as there's no clear fanning out or cone-shaped pattern. So the potential outlier warrants further investigation. It's crucial to examine the data point corresponding to this outlier to determine if it's due to an error in data entry, a truly unusual observation, or some other factor. If it's an error, it should be corrected. So if it's a genuine outlier and its inclusion significantly affects the model results, consider whether to remove it or use robust regression techniques. So it's important to note the interpretation is based only on this single residual plot. A comprehensive model assessment requires examining other diagnostic plots. So that's how we conduct our multiple regression analysis using Jamovi. Okay, so thank you for watching, everyone, and God bless.